There's a lot more to talk about in terms of how to find the parts for proving triangles are congruent, and sometimes triangles are overlapping, and how do you use those parts that are there but are really difficult to visualize. So part of this practice is teaching you how to take diagrams apart, put them back together, really search around, eliminate the possibilities, and also consider all points of view. So let's go play another game tonight. Go to geometry and go to overlapping triangles. And you're going to get this message about the Purloined letter. Did you ever hear of the Purloined letter? How to asks you. And it tells you in one of the Sherlock Holmes stories, a purloined or stolen letter is hidden in plain view among other letters, and everyone who is looking for it cannot find it. So, for the sake of evidence, this is not exactly true. The Purloined letter is a story by Edgar Allan Poe. It does not contain Sherlock Holmes, but it is a story of deductive reasoning, and I will post this link to tonight's homework page in case you want to read the story. It's a good one, and it's worth reading. It was later made into a video, short movie with Sherlock Holmes. So Sherlock Holmes has certainly been associated with the idea of this purloined letter. So the letter was stolen, and then it was hidden in plain view, which made it very difficult for detectives to find it. In this program, you are to locate the purloined parts. Those are the pieces that have been given to you, but they're kind of hidden in plain sight. You're looking for overlapping parts, vertical angles, and the application of the isosceles triangle theorem. In other words, if you have two base angles that are congruent, then their opposite sides must be congruent as long as they're in the same triangle. Or if you have a pair of sides that are congruent in a triangle, you've got opposite angles that must be congruent. So that would be an application of the isosceles triangle theorem or its converse. Just like we found parallel lines by establishing that alternative angles were congruent today, we can also find alternative interior angles given parallel lines. So you can use these things backwards and forwards. Click on examples to view the drawings before you begin. So when you get into how to, you can click on examples, vertical angle pairs, these are the kind of figures you're going to be looking at. So let's try a couple. These are the triangles you've been asked to identify, and you're looking for the purloined parts. What part do you think is hidden in plain sight here? You get to choose which one of these parts is going to be important to you. Angle A is congruent to angle A. That's really not important at all to proving that DEB, or triangle DEB, is congruent to triangle EDC. Let's take a look at the triangles separated using this link. So we're trying to prove that the blue triangle is congruent to the yellow triangle. This is very similar to one we did in class today. So which of these is the purloined part? The fact that DE is congruent to DE was the part that was hardest to see. That was the part that took the most discussion. So let's list that with its reason and ask for a new problem. So which piece is going to be the difficult piece to see? What is the purloined part here? Let's look. Let's see what happens when we click on Hide Extras. So based on the list of parts, vertical angles, common sides, common angles, or extra parts, let's take a look at what the purloined part possibilities are. Which of these do we have? Think the vertical angles here. We're looking for a pair of angles with P in the center. DPA is congruent to CPB. Let's see if that will do it. And let's keep looking for purloined parts until we've kind of exhausted what we've got here. Hide the extras. You need to make a decision about what the purloined parts or the parts hidden in plain sight are. Let's take a look at the two parts together. We need to make a decision about what the tough part to see will be here. Very often your triangles will be delivered to you in an overlapping way. Do we have any vertical angles here? Do we have any reflexive properties here? Do we have an isosceles triangle theorem here? Do we have the converse of the isosceles triangle theorem? These red lines from A to P and P to E indicate that A, P, and PE are congruent. So the part that will be difficult to see is that angle E is congruent to angle A. By reason, we've either got the converse of the isosceles triangle theorem or we have the isosceles triangle theorem. You've got to make a decision based on which one this is. Is it the theorem or is it its converse? Well, that's a pretty easy Google search. If you search isosceles triangle theorem and spell it anything close to correctly, you'll find lots of information on the isosceles triangle theorem. Wikipedia tells us that the isosceles triangle theorem states that the angles opposite the two sides of an isosceles triangle are equal. Is that what we see? Or do we see the converse or the opposite? Let's check. Look at the two triangles separately. So what do we have here? Do we have vertical angles? Do we have the isosceles triangle theorem? Do we have its converse? Do we have extra parts, or do we have overlapping parts? So play this game until you are correct more often than you are incorrect, and until you feel like you are able to see these parts consistently. And then post your screenshot to Schoology.